Alright, cool. So this is AQA A-level chemistry topic 4 completely patterned, yeah, all of energetics pattern, yeah. Now listen up because you don't want to end up like this Walla down here, yeah, vexed that his A-level results were dead. So go do the summary question as well and the sheets videos as well, yeah, when they're out. Alright, calm. Let's get into it then, yeah. Endothermic reaction, yeah, and exothermic reaction. These are energy profiles, yeah. It's the same as in GCSE, very easy. Endothermic, you got the reactants energy, yeah. And the energy of the products is going to be higher than the reactants because endothermic you had to put in energy, right? So now the system has more energy, so therefore it's going to increase here. So the products is more than the reactant, yeah. And obviously the activation energy is how much was needed to actually start it, right? And that's why you have the sudden increase. And then here again, so here same thing, yeah. Exothermic, you release energy, so therefore the products is going to have less than the reactants here. So then the reactants come, they're a bit higher, and then the products are down there, yeah, easy. Enthalpy, yes, this is what's new, yeah. So enthalpy, yeah. So when objects are heated, they use energy to expand, yeah, deeper. If you got a can of empty air of air, yeah, and you like heat that can, yeah, the air particles, the molecules, they're gonna be like moving away from each other, right? More energetic, moving away from each other, yeah. And that would increase the volume. That would cause it to expand, yeah. And so enthalpy encompasses the internal energy, yeah, as well as the energy used in expansion, yeah. So energy, yeah, is not like it is heat, yeah, but essentially, but it's not just the heat of the actual like internal thing, right? It also takes into account the heat, the energy used to expand it as well, yeah. So that's why we measure enthalpy and not heat, yeah, because energy um doesn't take into account the energy needed to expand it, yeah. If you were going to measure the energy as well, you would have to keep the volume constant, which is experimentally difficult. Yeah, deep it is kind of hard to keep the volume constant. Yeah, because the volume might change even a little bit, and you wouldn't know. Yeah, but to measure enthalpy, you just need to keep the pressure constant, which is a lot easier to do. Yeah, enthalpy change is heat absorbed or released by a system at constant pressure. Yeah, during an exothermic reaction, heat energy is released from the system to the surroundings. Therefore, yeah, we call it negative delta H. Yeah, delta means change, yeah, and H is enthalpy. That's what we call it. Yeah, that's a symbol. Yeah. So during exothermic reaction, yeah, heat energy is released from the system to the surroundings. So yeah, so because of this decrease, it's going to be negative delta H. Yeah, because there's decrease of enthalpy in the system. Yeah, it got released. Energy got released. Yeah. During an endothermic reaction, it's the opposite. Yes, positive delta H. Yeah, because enthalpy of the system is increased. Yeah, the system had heat added to it. Calm. Delta H can also be represented here by energy to break bonds plus energy to make bonds, yeah? So to break bonds, you need to put in a lot of energy. You need to put in, so you're putting in enthalpy, yeah? And then to make the bonds, yeah, once they're broken and I need to reform them to make the products, yeah, that's gonna release energy, yeah? So normally what you do if there's an equation, yeah, you check the enthalpy of the left and then you take away the enthalpy of the right, yeah? It's similar in GCSE, similar thing you'll see. Calm. The energy needed to break one mole of a bond here under standard conditions in a gaseous state is known as the bond enthalpy, yeah? So bond enthalpy, yeah, is how much energy you need to break one mole of a bond. So let's say a carbon-carbon bond here, covalent bond here, is how much energy you needed to break one mole of carbon-carbon bonds, basically, yeah, in a gaseous state. That's what bond enthalpy would be, and that value would be recorded here. Enthalpy change is measured under standard conditions of 100 kPa and 298 Kelvin, yeah, so that's what standard conditions are, yeah. The standard enthalpy of formation is the enthalpy change when one mole of a substance is formed from its constituent elements here under their standard conditions and state. So this is very important, yeah. Enthalpy of formation here is very important for Hess laws you'll see in a minute here, Hess diagrams here. And essentially what this is saying is this is how to form something from just the raw compound, right? So you go, you get some sodium, yeah, it's solid, yeah. You go, you get some chlorine gas, yeah. It's how much energy you would require from to go from just that solid sodium and that gas chlorine to make NaCl. Do you see? So it's the form of compound here based on just its constituent elements here in their standard conditions and standard state. Do you see? So not them being gas, not them being in the container together, nothing, just their raw standard state, yeah? And enthalpy of combustion is the enthalpy change when one mole of an energy of a substance here is completely burned in oxygen under standard conditions. Yeah, not we have to say completely. Yeah, because it's not incomplete combustion. Yeah, the one mole of substance has to be completely burned. Yeah, and keep remembering to say one mole as well. Yeah, you'll lose marks if you don't say that. I call mean bond enthalpies. Yeah, so different covalent bonds here require different amounts of energy to be broken naturally. Yeah, CC bond will be different to a CH bond. Yeah. Bond enthalpy values that are found experimentally differ from the data book, as the data book values are averaged, yeah. So bond enthalpy is very easy, yeah. It's just this thing you've seen in GCSE already, the bond energy, yeah. So HH, you know, remember you have these in GCSE, and you just need to find the bond energy of the left hand side of the equation, take away the right. It's the same thing here. We just call it enthalpy instead of energy, yeah. And bond enthalpy values, this is a common question, yeah, like a 1 marker, 2 marker. They'll be like, oh, why is why did the Don get a different thing compared to my man, yeah, compared to the data book value, yeah. And the reason why is because the data book value is an averaged value. So what they did is they took the CC bonds in like many different compounds, yeah, and they saw how much energy was needed to break it in the different compounds, and then they averaged it, yeah. Whereas if you do experimentally, you're only gonna like have it done once. Do you see what I'm still trying to say, yeah? So of course it's gonna be different from the data book values because the data book value is average value, yeah. It's not the experimental value. Bomb calorimetry, yeah. A sample of a compound is burned in a sealed vessel, yeah, and temperature change is measured. So, however, it can be inaccurate due to heat loss to surroundings, any incomplete combustion, and loss of reactant that evaporates before actually combusts. So, essentially, all that happens here is you put the sample here, you combust it, and then the water will basically heat up, and the thermometer will measure the heat change, yeah. So this allows you to find the heat change, which will allow you to find the enthalpy change. Now, finding enthalpy change, yeah, I got this little diagram here, yeah, because I got the thing on the right. So Q equals MC delta T, yeah, that's the equation you need to know about. So T delta T, that's what you found from bomb calorimetry, yeah. Then you times it by M and C. M is in grams, yeah. M is the mass of the water, not the compound, yeah, obviously, because above the water is the thing that's being heated up, yeah. And the water is what the thermometer is acting on, yeah. So you gotta keep it relative in it. The thermometer, the delta T is not delta T of this sample, yeah, it's delta T of the water. Yeah, so that's why I take mass of the water. You don't take mass of the sample that's being burned. That doesn't make sense. Yeah. And then you find Q. So when you do that, you find the energy. You find Q, yeah? Heat energy, yeah? Then when you find Q, the energy, yeah? What you need to do then, yeah, is you need to divide it by the moles, because that's what enthalpy will be. It will be the heat energy divided per mole. Heat energy per mole. So therefore, yeah, for heat, yeah, so you want to find Q, you just find the moles of whatever compound you're using, and then you just divide Q by the mole, and that's it. It's very easy, yeah. And so yeah, delta T is temperature final minus temperature initial. Kelvin is just Celsius plus 273. Grams is just kilograms times 1,000, yeah, and then joules is just kilojoules times 1,000, yeah. So yeah. Other calorimetry, any reaction that can be done in a sealed vessel can be measured, yeah. So enthalpy change of neutralization of an acid-base reaction can also be measured, yeah. This takes place in a solution inside the vessel, yeah. So you get the solution of the acid base and you put it inside the vessel to make sure it's constant pressure, and then yeah. The graph, yeah. So heat is always being lost from the calorimeter. So hence, just taking the final initial temperatures and finding difference is inaccurate. Yeah. So you might think, oh, I can just find the final and the initial. You know what I'm saying? Yeah. That's not correct. Yeah. I'll show you what you need to do in a minute. I'll show you what I mean as well if you're not understanding. Yeah. So if I'm not being clear. Yeah. So initially, yeah, the temperature of the reaction mixture may not be in equilibrium with the surroundings, calm, and then there may be a gap. So when the actual reaction happens here, it's really hard to like tell. It's not continuous. It's hard to tell. It will just go from like a low temperature to a high temperature as soon as the reaction happens here. It's not obvious, right? And you're not gonna be able to collect enough data points. So you don't really know where the reaction started and where it ended. That's really hard to do. You can take intervals here to like make it more accurate, yeah, but you still don't really know. And as a result, yeah, there's gonna be heat lost here during the reaction. So I'll just show you here. So this is before the reaction, yeah. So before the reaction, yeah, we're down here. Calm. Forget about this that's been extrapolated, yeah. So the final point would be here, and the final point would be there, yeah. So here's the reaction. It happened, and now look, this is the next point, data point, and then it goes down, yeah. These data points, yeah. So I can't just take this data point where my mouse is here as the final temperature, and this one here as the initial. That wouldn't make sense. I can't just do that minus that, yeah. That wouldn't make sense, okay? So what I need to do, yeah, what I need to do because that's not what the reaction happened, yeah, is I need to extrapolate the line. Extrapolating, yeah, means to basically extend it based on the trend. So I can see the trend is like that. So I can draw a line of best fit like that, and I can extend it all the way up. To extend it, that shows you the theoretical highest temperature that it was before the reaction lost any temperature, yeah, lost any heat. That's what the temperature would have been. Do you see? And then you take the difference between this extrapolated line up here and the temperature down here. Does that make sense? So that's what you need to do. Temperature before reaction, temperature after reaction. You extrapolate up here, extrapolate down here if needed as well. And then you find the temperature difference between them. Does that make sense? So that's basically is where these two meet, yeah? That's where the reaction would have happened and ended because it's instantaneous as you see. The energy just goes up straight away, the heat goes up straight away, yeah. So yeah, so that's what you need to do to make it to account for that temperature loss, yeah. So to estimate true temperature change caused by a reaction, researchers extrapolate the temperature change data back to the point where where there's zero heat loss. This extrapolated value represents the idealized scenario where all the heat released or absorbed by the reaction is retained within the calorimeter, yeah. Hess's law. So the overall enthalpy change, yeah, of a reaction is the same regardless of the route taken. So what he's saying, yeah, is you can take, M25, whatever, fam. There's different ways you can go somewhere, yeah, but essentially you're going to the same place. So because energy has to be conserved, yeah, if I go from A to C and then C to B, it's the same energy as going from A directly to B, yeah. So the delta HT, the total enthalpy, yeah, is the same as the enthalpy from A to C plus C to B. So that's all this is saying. It's very easy, yeah. Formation, yeah. So if I have the constituent elements down here, yeah, and I want to find how much to go from C to B, how much to form B directly from C, yeah. A might not be the actual elements; it might be like the elements in a gas state, yeah. But C might be the raw elements. So I want to find how much from C to B. What I need to do is I need to go from C to A first. So I need to think how can I make C into a gas, yeah, and then go from A to B. So from the gas and then to the actual product, yeah. So you'd go from delta H1 plus delta H, this one up here, yeah. So and if you want to go the other way, if you want to find how much from A to B, yeah, and that would be the same as delta H2, yeah. So from C to A and then A to B would be the same as C to B, yeah. And if I'm trying to find delta HT, so if I want to find that, yeah, what I can do is I can go from C. What I'd have to do is I'll have to go from A to B. So I'd have to go from A to C and then C to B, yeah. Now, A to C, I can just flip this arrow. This arrow is going from C to A. I can flip the arrow from A to C. If I flip the arrow from A to C, it becomes negative, yeah? So it becomes negative H1, yeah? So negative H1 plus H2. Does that make sense? Like vectors, yeah? That's how this works. Combustion. So I'm going to combust A back into this, like H2O and CO2. Same way I combust B, it will give me the same product here. It will be different moles of it, yeah? Basically the same thing. Anything that combusts completely will turn into that. So here, yeah? Again, it's the same thing. So let's say I want to go from A to B. Yeah. I'm going to go through delta H1 normally, and then I'm going to have to reverse this arrow. So delta H2, I'm going to have to reverse it. So it's going to become negative delta H2, so I can go up. Does that make sense? So that's all there really is to it. And that's it. A very easy topic, yeah. Go to the sheets, all of that, yeah, and you'll see his pattern, man.